All right, let's get into the good stuff. So 3.5, we're going to talk about transformations of functions. So a lot of this class, we're kind of talking about how does the graph relate to the algebra, relate to the word problem. Okay, so that's kind of some of the major goals. So we're going to talk about graphs in general. Now, this doesn't apply to just some graphs. This applies to every graph throughout class. So you can take a toolkit function, which you can find in your textbook. They are sometimes in some sources called parent functions, and I tend to accidentally interchange those all the time, so I apologize for that. But just know they're the same thing, right? So we have toolkit functions. We have a toolkit function for a quadratic. We have a toolkit function for a linear function. There are toolkit functions for absolute value. There are toolkit functions for rational functions, etc., etc., etc. Okay, so we have toolkit functions everywhere. It's just a matter of figuring out, once I have that function, then what's going to happen. Okay, and all of these functions can be transformed. And we transform them using four major transformations. Okay, so over here on the slide, you have the one example we're going to work with the most, well, at least at the beginning, so that we can kind of get our sea legs here. So we're going to start with absolute value. And the reason we start with absolute value is because it's symmetric and it has a very distinct shape to it. So it's really easy to tell where it has been moved to. So the parent function, or the toolkit function for an absolute value, is the square root of x. And once I've got the square root of x, I can then apply four different transformations based on what I want to happen. Okay, so if I want that graph to be twice as tall, I put a number out front where the a is. And whatever number is there is going to tell me, make this graph taller or make this graph shorter. It is also considered, so that makes it, a vertical stretch or a vertical shrink or a vertical compression. They use those interchangeably as well. If the a value is negative, that graph is going to flip over vertically, so the top to the bottom. Okay, a horizontal stretch or shrink, if I want to make it wider or skinnier, I put that number in the c value, which means it goes inside the absolute value. Okay, really subtle difference. Outside the absolute value is an a, inside the absolute value is a c. Okay, a negative value in the C location flips that graph horizontally. Okay, so it's going to move it this direction in the flip. It's going to go around the y-axis or around the center of that graph. Okay, if I want to move the graph left or right, I put a number where h is. If I want to move the graph up or down, I put a number where k is. And depending on where those numbers are, they're going to do what they say or they're going to do the opposite. Okay, now by opposite I mean everything that is inside the toolkit function with the x value. Okay, if it is attached to the x value, it's going to do the opposite of what it says. Probably spelled that wrong. Okay, but it's going to do the opposite of what it says. Meaning that if I have a x minus 3, it's actually going to go to the right. If I have x plus 5, it's actually going to go to the left. And the reason for that is because this is set up with a negative sign. So it's set up to do the opposite thing. And what that kind of thinks of is like, if I put a 5 there, how do I get back to where I started? So if I want to go plus 5, well, I have to go minus 5 to get back to where I started. So it kind of sets us up to work in reverse or work with inverses, which is what we'll do in 3.7. But it sets us up here for now so that we have an idea of where we're going, what we're looking for, how do I get there, all of that good stuff, okay? The C value, again, does the opposite of what it looks like. So a C value of 2 isn't going to make it wider, it's actually going to shrink it by a factor of 2. A C value of 1/2 isn't going to make it skinnier, it's going to make it wider. Okay, so The good news about that is we don't use c-values very often, okay? Particularly in this class. There are a couple of places, and when we get to those places, I'll let you know and remind you about the c-value and what it does. But for the most part, we don't really use them. And the reasoning for that is because with most of these basic toolkit functions, there is a mathematical way to factor out that c-value, and you have to do it kind of carefully, but you can factor out that c-value and you can combine it with the a value. You can multiply them together and then just treat it like it's an a value. Okay, so the c-value exists, it's useful. We're going to come back to it. When we first start out with these, we're going to mostly talk about A's, H's, and K's, right? All right, so if my job is to find the toolkit function, okay, so I have x minus 3 squared minus 5. If I want the toolkit function, the first thing I need to do is decide what are A, H, and K. And I know that sounds backwards, but this is how it works. Okay, I have x minus 3, which means this is H, minus 5, which means this is K. So if I change everything and I get rid of the H and K, so if I pretend that there's zeros, then all that's left here is an x and a squared. And so f of x equals x squared is my toolkit function. Okay, it's what's left if I take away all the transformations. So in the first one, my toolkit function is x squared. Now the transformations, h is 3, k is minus 5, or you can think of it as h is negative 3, it's fine, okay? However, you have to kind of word that in your brain so that you're making sure you're doing the right thing. H is 3, which means we're going to the right 3, right? This is a minus 3, which looks like it's going to go left, but it does the opposite. So it's going to go to the right. And then this k is negative 5, which means it's going to go down 3. Okay. With the x is horizontal. Outside of the x is vertical. With the x means it's on the x-axis, and the x-axis is horizontal. Outside of the toolkit function means it's attached to the y, or the vertical axis, which means it's going to go up or down. Okay. F of x is negative absolute value of x plus 2 plus 6. Okay. A is negative 1, right? If there's no negative sign here, A is just positive 1, and if A is positive 1, it doesn't do anything. So we often just kind of skip over it, like I did in the last example, because a positive 1 doesn't change anything. So it's not going to do anything in terms of transformations. If it's a negative, I need to make note that A is negative 1, because what that does is causes this function to flip over vertically. Okay, so instead of facing upwards like this, it's going to face downward. Okay, and I know I haven't shown you the shape of an absolute value, but that's the basic shape. It looks like a V that holds water, unless I flip it over and then it's a pyramid. Okay, now I've got an H in here, so H is actually a negative 2, because remember, I'm supposed to have a minus sign right there. So this is going to go to the left 2. And then I've got a 6, so k is positive 6, which makes this graph go up 2. Now if I take away all of those transformations, right, I make a positive 1, I make h 0, I make k 0, then what's left is the absolute value of x, which makes that my toolkit function. Okay. So the transformations are the numbers that are in the place of a, h, and k. The toolkit function is what would be left behind if none of those were there. Let me erase this one. All right, f of x is 2x minus 7. Okay, two things. Number one, I've got an a. It's a positive number, which means I'm stretching it by a factor of 2. So this is going to be, we call them a vertical stretch by 2. Okay, so it's going to be twice as tall. Now you might recognize this already as slope. Slope and a are the same thing. It's just that lines, these linear functions, are so common that we tend to talk about them in a slightly different way, so that when we're talking about lines, the idea of slope is easier to link to this idea of a vertical stretch. Okay. Now, I've got this minus 7, and the next question I have is that an h value or a k value? The answer is that's a k value. Okay. K is minus 7, which means we're going to move this down 7. And you might also recognize that specifically as the y-intercept. With that y-intercept, I'm taking a function and I'm moving it up or down so that I can get to the right place. If it is an x value, the function would have looked like this. Okay, if it is inside that parenthesis, it's a h value. If it is outside of a parenthesis, it's a k value. All right, now if I remove a and k, then my toolkit function is just f of x is equal to x. And then that function gets kind of moved around and shifted all over the place and becomes every other linear function you've ever worked with. Okay? It can have an a value of a fraction, it can have a positive, it can have a negative, it can have anything it wants. Any other variation is just that function moved around. All right. f of x is 3 times the square root of x plus 8 minus 7. Number out front. Got an a value. A is 3, which gives me a vertical stretch by a factor of 3. So we just say stretch it by 3. Now there's no parentheses here, but there kind of is. They just look funny and they're kind of hidden. There is a parenthesis here, but we indicate it by just drawing this square root over the top of both places. And since it's over the top of both of those places, that's considered inside or like a parenthesis for the purposes of transformations. So we call that a transformation that is inside with the x value. So this means that h is negative 8, and we're going to go to the left 8 places. Okay. Now lastly, I've got this minus 7, and notice how the square root ends right here? That means the minus 7 is outside, so that's a k value. So k is negative 7, and that is going to shift this whole thing down 7. Okay. Now, the parent function here, or the toolkit function. If I take away all of the algebra, all the numbers that are happening, then I'm left with a square root sign and a variable. So my toolkit function is the square root of x. All right, we've got one more. And the last example here is just to show you that you don't actually have to know what the function is. You don't have to know how it works to understand what the transformations are doing. Okay, this last function is -3 times the cosine of x minus 4 plus 5. Now, cosine is a trig function, and if you have to take trig because you're going on to calculus for honors college or calculus for your major, or you're going on to physics, or you're going on to other STEM fields, great, I'll see you in trig. But you don't have to know this until then. Even though I don't know what cosine is, I can figure out what the transformations are. We have a -3 in the a value, which means I'm going to flip it vertically because it's negative. Right? Negative numbers flip over. Let me give myself enough room here, sorry. So I have a vertical flip, and then I'm going to stretch it by a factor of 3. So I flipped it over, and now I'm going to make it taller. Okay. Inside the parenthesis, I find an h value. H is 4, so we're going to go to the right 4 places. And then outside of the parenthesis, I've got a k value of 5, which means this is going to go up 5 places. Now the toolkit function, which is left over when everything else has been kind of removed, is f of x is the cosine of x. Again, I don't need to know what it is. The toolkit function is whatever's there once the numbers are gone. Okay. So those are the 3 major transformations we're going to focus on for now. We will come back to that c value when we need it. I don't have to know what the functions are even. Okay, we can describe all of these transformations, we just don't necessarily know what the toolkit function is, right? If I take away all of the numbers here, my toolkit function for all of them is f of x. And that's the best I can do. Okay, it's the only thing in all of these once you take the numbers out. So my toolkit function is f of x. So then let's look at the transformations. So pause this for a second. Write down your transformations, write down what you think is happening, and then push play and you will have the answers. Okay. So f of x plus 3. The plus 3 is outside of the parentheses, so this function is going to go up 3. I have f of x minus 3. Now that minus 3 is inside the parentheses, which means it's an h value. So we're going to move horizontally to the right 3 places. Okay. F of x plus 1 minus 5. The plus 1 is inside, so it's going to go to the left 1. The minus 5 is outside the parentheses, so we're going to go down 5. Okay. Negative f of x plus 8. The negative sign out front is going to flip vertically. Plus 8 means I'm going up 8. And then this last one, I'm going to go vertical stretch by 2. The minus 3 is inside parentheses, so I'm going to go to the right 3. and then I've got minus 4, so we're going to go down 4 at the end of that. Okay, so you don't have to actually know what the function is. The goal is to just be able to identify those 3 numbers in those 3 places and figure out what that means for my graph. Okay, now odd and even functions. In order for a function to be considered odd and even, we are actually not talking at all about the powers involved, about any of the toolkit functions specifically. We're not talking about anything other than what this actually means is a type of symmetry. Is it symmetric? And specifically, is it symmetric in 2 types of places? Okay, the first one is if a function is even, it has vertical symmetry on the y-axis. So, common examples are quadratics or absolute values. Those are the most common. It doesn't mean they're the only ones, but they're the most common. Now, the problem with this is if it's even, and I take this function and move it either to the left or to the right, it's not even anymore. I've ruined it because it's not that it's vertically symmetric, it's that it's symmetric on the y-axis specifically. Okay, and if it doesn't have that symmetry right on the axis, we pretend it's not there. Okay, now it's odd if for every input value we have rotational symmetry on the origin. Now what that means is, say I have a cubic function, something looks like this. Imagine putting a little brad in the center there and then spinning it. Say I spun it around like that. It would land on itself. And so if I can stick it on that brad and kind of spin it in a circle and it comes back, then we're good. That's called odd. Okay, that is rotational symmetry. All right, so how do we figure out what it is? How do we figure out whether it's one or the other? We use algebra. So let's take f of x. Let me get my pencil. Equals 3x to the 4th. Now, what we do every time is we start by plugging in negative x. So we're going to substitute in f of negative x. So I have 3 times negative x to the 4th. Now again, exponent rules are going to come back and haunt you. The negative x is inside the parentheses. The 4th is outside the parentheses. So I'm going to take negative x times negative x times negative x times negative x, which is going to give me positive x to the 4th. Now, because these 2 things are exactly the same, that means that they are even. If I get the same answer when I plug in negative x, it's an even function. Right? Let's take f of x is the square, or sorry, g of x is the square root of x. I'm going to plug in negative x. So g of negative x is equal to the square root of negative x. Now, that's not the same thing, right? Because we know a square root of a negative number gives me an I value. So this is I times the square root of x. Okay, so these are not exactly identical, which means they're not even. In order for them to be odd, f of x has to equal, f of negative x has to be the opposite of f of x, which means exactly the same terms with opposite signs. So instead of adding, I'm subtracting. Instead of subtracting, we'd be adding. But all of the terms would be exactly the same. Okay? They're not identical. They're also not opposites. And because they're not opposites and they're not identical, we just say that this function is neither even nor odd. And in the real world, and if I look at the picture of every single function ever created, most functions are not even or odd. Okay, that's actually the most common answer. But because we want to show you the difference between the two, when you work in this section, you're going to see a lot of functions that are one or the other. Okay, and every now and then we're going to put in a not. But for the most part in this section, it's going to be one or the other. But every now and then, expect one that's not. So again, okay. All right, let's look at h of x. So h of x, we're going to plug in negative x. So I get 1 over negative x. I don't know why my pencil is acting like this. Plus 3 times negative x. Okay, that negative sign can come out front, so this is 1 over x, sorry, negative 1 over x, minus 3x. So I have exactly the same terms as the original, right? I have 1 over x, I have 3x. In the original, they were plus and plus. In my current function, they're minus minus. So that means that this function is considered odd. H of x is an odd function. G of x is x squared plus 3x minus 9. So we're going to plug in a negative x. So g of negative x is negative x squared plus 3 times negative x minus 9, because there's nothing to plug in on that spot. So negative x squared would be negative x times negative x, which is going to be positive x squared. 3 times minus x is going to be a minus 3x minus 9. Now it's not exactly the same as what I started with, right? This sign in the center has changed. So it's not exactly the same. It's not exactly the opposite. I have the same terms. I still have x squared, I still have 3x, I still have 9, but some of the signs are different and some of the signs are the same, which means it's also not odd. Okay, so this function would be neither even nor odd. Okay, now f of x is 5x to the fourth minus 3x squared plus 1. I'm going to plug in a negative x. So 5 times negative x to the fourth minus 3 times negative x squared plus 1. Negative x to the fourth is going to be positive x to the fourth after I multiply, right? Negative times negative times negative times negative is going to be a positive number. Negative x squared is going to be negative x times negative x, which is going to give me a positive x squared. Didn't plug anything into the last place, so it's going to stay as is. So when I plug in negative x, I get exactly the same terms with exactly the same signs, which means that this function is even. Okay, so we've got all of those scenarios kind of put into one, and that's how you test odd versus even. Okay, that's 3.5.